Morning, everyone. My name is Diana. I'm a PhD student at Brunel, supervised by Derek, and I'm just starting my third year. And today, in the next 20 minutes, I will talk about migration simulations. The main aspects that I will be going through within 20 minutes is that what is migration modeling? Why is it important? How do we predict refugee movements using a generalized simulation development approach? As well as how can we actually make it more efficient and less time-consuming using automation of refugee modeling using FET-HPC. Why do we explore parameters within refugee modeling, as well as I will touch upon what we've done so far in terms of uncertainty quantification and sensitivity analysis within the refugee modeling. And the other work that we've done so far is parallelization with multiscale modeling of refugee movements. So to start with, I want to highlight one of the main aspects that we face today is that in the world we have 71.44 million people displaced worldwide. So of which we have more than 20 million refugees, and we have almost 40,000 internally displaced people worldwide. And you can see that within the UNHCR statistics that mainly they are within Africa, Middle East countries, and in South America. So after knowing that refugee internally displaced people and refugees, exist within the news today. What do I do is that I explore techniques to predict forced migration, and within the forced migration, why do we do it? Is because human migration can be seen from two terms, voluntary or involuntary, which is the first one. And people usually displaced from their origin country due to internal or external conditions. One of them within the internal is the violence, which has the biggest impact that force people to go to other countries and seek safer places. There are other conditions such as worsening of socioeconomic conditions, famine, natural disasters, whereas external conditions involve colonization, global inequality, incorporation of local economics, and the deterioration of the environment. But main aspect within our research is the violence that force people to flee, and I aim to develop automated agent-based simulation predicting refugee movements. But you would ask, why is it? Why is it important to model refugee movement? Main aspect is that refugee movements matter, and it's important to be able to predict where refugees go due to three different aspects. First is that to save refugee lives, it helps the governments and the NGOs to allocate humanitarian resources efficiently as well as correctly. So we can say that if we know how many refugees are going to come to a certain camp, we can allocate those much resources towards the camps that we'll be heading to. Another aspect is to help complete incomplete data collections on refugee movements. One thing we face within our research is that there are a lot within the refugee movements, the data is incomplete, so we have to go through lots of difficulties within our research. And the last but not least is that to investigate the consequences of a nation closing its borders for refugees. So what happens if a neighboring country closes their borders, refugees, what they have to do, and how it impacts actually the movement of people. So next is how we predict refugee movements. In last year, we, in collaboration with Derek and my other supervisor, Dr. Derek Bell, we wrote a paper in a journal, and we developed a generalized simulation development approach, which was applied for 3 African countries. And how we did it? We took a country which was Burundi, Mali, or Central African Republic. After identifying conflict region, as I mentioned, 3 countries, you start to collect data sources. So APLET, which provides us violent places where conflict occurred. We have geospatial data, so from conflict zone towards the camps, how many kilometers, how how they should be distributed across. And we have UN refugee count, which provides us camp names of the neighboring countries, as well as they provide us how many refugees were in certain camps. After taking that data, we construct our initial model. We get from data source conflict zones, route constructions, camps, and the total number of refugees in conflicts, as well as in camps. After constructing our model, we can refine it using population data for each region, or as well as, you can say, for the region or the city that was affected with the conflict. We can also refine these border closures and forced redirections. By that, I mean that in some countries they have border closures, so we close a border within that country between two countries, so refugees can actually reach their camps. They have to go to other camps. And then we have fleet code. Fleet code is written in Python. It actually executes our simulation. After running our simulation, we get our results, and then we analyze them and validate. So if you want to get more into detail, we have a paper and the QR code.
It's an agent-based model.
Yes, it is.
So it has parameters in it which we may not be sure about.
So far, yeah.
Quite a few, yeah.
Because of the data that we have, which is incomplete, we face with lots of issues with the networks. After we generalized our model, we can construct different situations, conflicts. One thing that we were facing is the inefficiency and the time consuming that was to take one conflict. We had to construct each single model, and it was very time consuming. So what I'm working at the moment is try to automate all this process, all the phases that I mentioned earlier. So far, data source selection, it's manual, but we are able to construct CSV files. I'll talk more about it, and then it's more automated, semi-automated at the moment. We have model construction. As I mentioned earlier, we construct a single model, and then we have model refinement. So we generate models of a parameter or policy range using FabFleet, which is FabSim and incorporated with our FabFleet, so we get it FabFleet. We execute our simulations. It's an ensemble of executions, also automated at the moment. And then we have validation and visualization. We haven't touched upon that yet. So within the data extraction, well, first we developed a model building approach. So we have our four main sources that I mentioned earlier, right? From that, we developed four CSV files that we can incorporate in our initial model construction. That can be also helpful to construct network maps. Network maps allows us to visualize how refugees move from conflict and where the camps are located. And this model can be explained in more detail in one of the conference papers that I wrote. So construction of initial model is that we have, this is what I'm working at the moment, as I said, the automation part. I have 4 examples of conflict zones. We have source data for each of them, and then I use the 3 CSV files that I created using the data sources. So there are locations, which provides me all the locations within which I have camps, conflict zones, or other intermediate towns that connect these 2 main aspects. And then I have routes that are given from node 1, node 2, how many distances. And then closures. If there are any camp closures or border closures, we also can incorporate that within our simulation. So let's say that I'm working in South Sudan model. What I do now is that I have this CSV file. I load my conflict by using fab localhost load conflict. And when I use that, I can automatically do any other parameter explorations, which can be easily recorded within active conflict. But it will not touch my initial source files. So they can be used for any other instances, let's say. Like at the same time, if you're done with that conflict, if you want to do any others, you just clear active conflict, you have that command and it generates the from scratch. So within the model refinement, is an exploration parameters for policy decisions. What is important, why is it important, is to examine policy implications that can vary across conflicts. So let's say that there are different aspects within the conflict. For example, in South Sudan there can be camp closures, whereas in Burundi there can be border closures. So you have to incorporate to all of these parameters. What I've done is I've developed 6 parameters so far. So we have change camp capacity. When camp capacity gets filled up, then we have to make sure that we incorporate that within our simulation. That's why I have change camp capacity command that can be used. It's all automated, as I said. And then we can add any new camp if you want to within our simulation. If you find it at a later stage, if we haven't found it, for example, at the beginning of our initial model construction. We can also define our model by deleting any location. If let's say that one of the locations wasn't that important or it had less effect on people moving towards the camps. And then we have camp closures, border closure, and forced redirection. Forced redirection is when from one camp to another people move. So if one camp gets full capacity, they are moved to another camp which is next by. So after identifying all these parameters and they are automated, we can easily change or modify our model. And after modifying our model, what we do is that we execute our simulation, which is done by easy command, have localhost instantiate, and then we run our simulation using flee, which is flee, and then the conflict name. So having lots of instances, you can have ensembles of executions. So by using different, for example, if we just change camp closure, and then we can instantiate that as well as we can run it, and we can have our results. Next example can be that there's a force redirection within a certain camp. We can actually analyze what kind of difference it gives us. With different parameters, how our results are changed, or what can we see within different parameters. What kind of policy decisions can be made out of that. At the moment I'm working on South Sudan model, and I'm applying all these automation tools within the South Sudan model. South Sudan model has a simulation period of 604 days. So it started from 15th December 2013 till 10th of August 2015. South Sudan is one of the highest impacted countries that has refugees at the country. It's still ongoing conflict, as well as they have lots of refugees fleeing from that country. But it was a big simulation that I had to do. That's why I had to take a part of the conflict, which is from 15 December 2013 till 2015. So far, I got 24 conflict zones. You can see within this network map, the red dot identifies the conflict zones, as well as I have camps which are located in neighboring countries, in Ethiopia, Kenya, Sudan, and Uganda. And there are over 800,000 refugees by August 2018, according to statistics and results. So after I explained everything what I did, this is one of the things that we've done so far within the refugee modeling. One aspect is uncertainty quantification and sensitivity analysis. Bachelor student within our university has wrote a dissertation on uncertainty quantification, and he tried to identify what kind of uncertainty we have within the data. So we have, he used this approach, as you can see on the left. He identified by applying one factor at a time sensitivity analysis. He's run a simulation, evaluated, and then if he expected the results that he needed, he replaced the input result. So it can, there can be a change within the output, or he used the nominal. This is the result that he got. So you can see that more higher the number of refugees increased, the error margin decreased. However, when he increased the refugee numbers by 50%, it actually gave the error margin increase. So you can understand that input data actually has uncertainty towards the output data. So, parallelization. That's one of the works that's recently done by Derek, and he attended the conference and presented the paper. So what we have here is the total number or processes given by self-MPI size, and we have the rank of current processes by self-MPI rank, and then the sub-agents appended per location as a person. So this speed-up plot on the Archer supercomputer on the EPCC in Edinburgh using up to 1 node 24 cores. So you can see that speed up to 15 M is like around 8.
Yeah, can I say something short?
Yeah.
So this is basically, it's a Python code, and parallelization is a total prototype. I think it's probably about day coding it. We can get that line up, but basically this is our first attempt because at the start of the project we wanted something that at least scales to some extent on a single node. So that is what you see here.
And another aspect of refugee modeling is multi-scale coupling. So at the moment, using FLE, we can achieve macro-level macro model simulations. What we also would like to achieve is micro models and the coupling and the parallelization. So at the same time, we have sensitivity analysis presented in our scientific reports paper. What we would like to do within the VECMA as well, within the refugee modeling predictions, is that we're going to achieve how data uncertainty can be quantified, as well as rule out uncertainty quantification around our input data, and do uncertainty propagations. So these are all what we want to get in the next couple of years. And this is within Derek's paper as well.
If you want, I can have a few short comments on that. So basically what we did is a micro model, macro model, just toy models, or simple models basically, coupled together at the moment using file exchange, and then based on a single node do a short test to see whether the exchange works and how it scales. What's quite interesting actually is that on a normal desktop, if you overpopulate the nodes, so you use twice the number of processes compared to the number of cores, you actually get better performance because the refugees go from one model to another. So one model becomes more compute intensive, the other one becomes less compute intensive. So if we want to map this to a supercomputer, we might actually want to consider overloading the node. So that's, I think, is relatively unique in this application.
So, and last is the references. So, yeah.
Great, thanks very much.